Okay, so to recap, we have seen that the universe, if you add up all the matter in the universe that we can see, and all the matter in the universe that we can't see, all the normal matter, all dark matter, you get to only about 27% of what you need to have a flat universe. And yet, geometrically, the universe must be flat. So there's some piece of the puzzle that we're missing. What is that piece to the puzzle? Well, the clues started to come in as we were measuring the distances to distant galaxies. So I promised you that we'd come back at the end of the semester and talk about why these type 1a supernovae were so important, and that day has come. When you look at type 1a supernova, here you have three weird looking galaxies in the top. These are all fairly distant galaxies. It's the blue thing here on the left. It's the red thing here in the middle. It's the it's actually this orange thing is the galaxy. This is an elliptical galaxy. Anyway, in the bottom pictures, you see a supernova that has gone off in each of these. These are all type 1a supernovae. How do we know? Well, we take a spectrum of it, and what absorption lines we see, and also the shape of the light curve tells us what kind of supernova it is. And the type 1a's, remember, are white dwarf progenitors, where you're dumping matter onto the white dwarf, and eventually it explodes. It exceeds the Chandrasekhar mass limit, collapses, and explodes. And these all have exactly 1.4 solar masses, and so their brightnesses, the luminosities, their intrinsic brightnesses, are all exactly the same. And so you can tell how bright these things look, by how bright these things look, how far away these things are. And so once you know the distance to one thing in a galaxy, that gives you the distance to the galaxies themselves. And so we can map out peculiarities, curves in the Hubble flow, and track how the expansion rate has changed over time. And that should tell us which of those curves we were on before. The one that goes straight back, you might remember, the one that curves down really quickly. I'm going to show you on the next slide anyway. So which one is it? Do we live on the recollapsing universe? Do we live on the coasting universe? Do we live on the critical universe? This should tell us which of those curves we live on. And the answer, amazingly, is none of the above. So let's just recap. This is the average distance between galaxies. You can call it that R parameter we used before. It is a parameterized size of the universe as a function of time, right? And so again, the blue, green, and red curves are the ones we saw before. The blue curve is a one that has no matter in it at all and just expands at a constant rate for all time. The red one has omega greater than 0. This is a closed universe. This one will eventually recollapse on itself. And the green line is the critical universe. This is the flat universe. We know that our geometry must be this. But we know, and we can see, and if the data, so this is where the supernova actually lie, and how far in the past they look back. And so if we lived on that actual flat universe, they'd be over here. They are not. They are on the best fit data to neither the blue nor the red nor the green curves. There is a fourth possibility that we haven't even talked about until now, which is that maybe normal and dark matter are not the only constituents of the universe. And in fact, we happen to live on a curve that implies that not only is the universe expanding, but that expansion rate is actually getting faster. And we expect that this expansion rate will, instead of slowing down, actually accelerate. That's the weird thing about this whole thing. So what the heck is going on? Well, to understand what's actually going on, we need to think about Einstein and what he was thinking when he first put together his theory of general relativity. Remember, the theory of general relativity is the one that includes curved space-time, right? This is the thing near a black hole where, and anything really that has mass, why does the moon and the Earth exert forces on one another? It's because the Earth, as a very large massive object, warps the space-time around it. And the moon is trying to travel in a straight line, but it's got a curved path, and so it's forced into this elliptical orbit. Einstein realized shortly after he published this result, his theory of general relativity, that it had amazing implications for the universe itself. He realized that it was his theory of space-time and his theory of gravity could not accommodate a static universe. Let me say that again. His theory, where space-time is curved, could not explain a static universe. And at the time, we're talking about 1917, this is way before the Hubble law had been discovered, that was the prevailing understanding of scientists about the state of the universe. If you'd asked a scientist in 1915 how old the universe is, 9 out of 10 of them at least would have told you the universe is infinite. It has always been here. It will always be here. It's always looked about the same. It will always look about the same. Einstein was comfortable with this. He was happy with this. He didn't want it bothered him that his theory then seemed to contradict this, because according to his theory, that was not a possible state for the universe to be in. It had to be dynamic in some way. It had to be expanding or contracting in some way. And so to save the idea of a static universe, an infinite universe, Einstein added something to his theory. It's the equivalent, if you're a math person, of kind of like an integration constant. It doesn't change the theory. It's allowed, but there's no motivation for it other than to match the physical description of the universe that you want. And so he called it the cosmological constant, and its effect is, so he knew that his theory and the matter in the universe predicted that if the universe were stationary, if it weren't expanding or contracting, that it would naturally want to collapse back in on itself. And so this cosmological constant provided a counterforce. It provided a force that counteracted the universe's natural tendency to want to collapse in on itself. It was a repulsive force, if you like, in the universe that counteracted the gravitational force. If you tuned that parameter to exactly the right value, then it could exactly offset gravity, and you could have a static universe that was neither expanding or contracting. Of course, some 10 years later, Hubble goes out and discovers that, in fact, the universe is expanding, and Einstein does one of these. No, I could have predicted that. My theory predicts that that should be the case. So he later called it his greatest blunder, adding this constant to his theory to predict what he thought the universe was like. He had a chance to predict that the universe was in fact expanding, and he didn't do it. So he didn't make many blunders, but that was certainly one of them. Well, he considered it one of them. Now, fast forward 100 years, where are we? Well, now we need some force that is pushing outwards and causing the universe to accelerate. So his greatest blunder might have been true and needed after all. And it seems to be like some sort of cosmological constant force is acting on the universe. Let's go back to the previous slide, to cause it to accelerate. There has to be some sort of vacuum energy or something that is acting and acting more and more prevalently as we go forward and acting as a repulsive force. Okay, so what is it? What is this thing that is out there and is causing the universe's expansion to accelerate? Well, the answer is we don't know. Here it is, 2020, and we still don't know. So that's pretty crazy. But think about this. Let's just put this all out there so we can see it. Oh, look, it's me. I didn't really want to be showing me. Okay, that's better. So let's recap. Again, we're talking about the normal matter in the universe. We'll call that omega m. That was 0.04, right? We're talking about the dark matter. Let's call that omega d. That was about 0.27. There's another constituent to this. It's not matter. We call it, it's this cosmological constant thing. We call it dark energy. Why dark? Because it doesn't emit any light, and we don't know what it is. I'm going to call that omega. This is going to get weird. This is a capital omega. That's a Greek letter lambda. Oops, that's an A. It's a capital lambda. And this is the symbol that is often used to denote Einstein's cosmological constant. So this is the symbol for dark energy, this omega sub capital lambda. And so this, it turns out, contributes to the energy budget of the universe. Remember, Einstein's E equals mc squared, mass and energy are equivalent. And so for the purposes of determining the geometry of the universe, dark energy adds up in the same way that these dark matter things do. And so if we're going to explain, we can sort of measure this. We sort of know. This comes out to about 0.73. And when you add all of that up, which you can do to do a geometry term, you get exactly 1. Or, you know, plus or minus 0.01 or so. And this is the missing piece. So the normal matter and the dark matter in the universe do only make up about 20, this is about 23%. This adds up to 27. This is 0.73. Adding all of these up gets us to almost exactly 1. And that gets us to a flat universe. And that's where we need to be geometrically. But these dark matter and dark energy do behave exactly the same in giving us what the geometry of our universe is. They behave very differently in determining what the universe's expansion rate and expansion history are. The normal and dark matter, all the matter in the universe, is an attractive thing, and it's slowing down the universe's expansion. This dark energy term is a repulsive force, and it causes the universe's expansion to accelerate. So all of those things that we were talking about before, about those 3 different possible universes, omega greater than 1, omega equal to 1, omega less than 1, all of those were not including anything that resembled dark energy. Including this dark energy puts all of those pictures off the map. And it's really a 4th thing now that we have to worry about. And that 4th curve is this one. So the answer is, which of these 3 we're on? The answer is none of them. We're on a 4th one that includes some weird dark energy thing that we hadn't considered before. And so this also, by the way, gets us back to our original roughly 14 billion year old history of the universe. So it happens to be that using the Costin metric to calculate the age of the universe was really good, because we happen to be on a universe where there is dark energy. We also think that this dark energy term is somehow related probably to the amount of space there is in the universe. It's some sort of vacuum energy. And so as the universe continues to expand, this dark energy term becomes more and more dominant and important. And so these are present day values of these. In the past, this dark energy term was less, and in the future, it will be more, a greater percentage of the total density of the universe. Okay, so I will end this class today. We will come back one more time next week on Tuesday to do our last class, and we will be thinking about what conditions were like in the early universe. We'll be thinking about other observational evidence that we have for a hot Big Bang, and be talking about what the ultimate fate of the universe is. So I look forward to seeing you then.